Sanjay, can I just check with you? Can you see just my slides or can you see the rest of the screen as well?
No, only slide, sir.
Okay.
Yeah, that's fine.
Because I have a few other windows open next to, which is the from WebEx.
Yes, no. Now it's only your presentation is visible only for us.
Just to make sure that nothing is sort of blocked.
Yeah. And then now we will start. So I request you, please, Mr. Ruchi, please start. Introduce your speaker to the participant, and then we start the lecture. Please unmute yourself. And then go ahead.
A very good morning to you, sir, and a good afternoon to all our participants from India. Hope you all are doing well. On behalf of IEEE NTC Student Chapter, I welcome everyone in the today's webinar from the series of webinar on the topic related to nanotechnology and neuromorphic computation. Today we are going to have Professor Themis Prodromakis, Director of Center of
Shall I start my presentation?
Sorry, sir. I think there might be some internet issue will be there. If you can just give us a minute, we'll be starting with this shortly. I think there might be some issue with the Ruchi at her end.
sorry for the interruption to all. Now I would like to introduce our speaker to all the participants. First of all, thank you, Professor Themis, for accepting our request for this talk. Professor Themis will deliver his talk on Memristive technology from functional oxide to AI on chip. So with your permission, I would like to give a brief introduction of yours to our participants. Dr. Themis is a professor of nanotechnology and director of Center for Electronics Frontier at the University of Southampton, UK. His work focuses on developing metal oxide resistive random access memory, Memristive technology, and related applications, and is leading an interdisciplinary team comprises 30 researchers with expertise ranging from material process development to electronic devices and circuit and system for embedded application. He holds a Royal Academy of Engineering Chair in Emerging Technologies and a Royal Society Industry Fellowship. He is an adjunct professor at UTS Australia, visiting professor at the Department of Microelectronics and Nanoelectronics at Tsinghua University, and honorary fellow at Imperial College London. He is a fellow of the Royal Society of Chemistry, the British Computer Society, the IET, and the Institute of Physics, and is also senior member of the IEEE. He also serves as the director of the Lloyd Register Foundation, International Consortium for Nanotechnology ICON, and co-director of UKRI Centre for Doctoral Training in Machine Intelligence for Nanoelectronic Devices and Systems, Slotley Mines. In 2015, he established ARCS Instrument Limited that deliver high-performance testing infrastructure for automating characterization of novel nanodevices in over 20 countries, and in 2019, he formed
meeting. Church.
participants. I request you to mute yourself. In 2015, he established ARC Instrument Limited that deliver high-performance testing infrastructure for automatic characterization of novel nanodevices in over 20 countries. And in 2019, he founded Sona.ai, that is building new power-efficient hardware solution. His contribution in Memristive technologies and application have brought this emerging technology one step closer to the electronic industry, for which he was recognized as a 2021 Blavatnik Award UK honoree in physical science and engineering. Sir, with your permission, I would like to give, sir, the floor is all yours, and I request you to share your screen. And participants, participants are requested to keep their audio in mute mode during the talk. Thank you.
Thank you very much for the very, very kind introduction. So today I'll be talking about Memristive technologies and the work that we've done that allows us to bring new functional oxides to develop solutions for allowing us to embed AI on chip. So before I start, I'd like to, hopefully you could see my screen, just to double check that everything is okay.
Yes, sir, your screen is visible.
Excellent. So for those of you who are not familiar where Southampton is, that's England. Here is London. Hopefully you can see my cursor. And here on the south, we have Southampton. Southampton is actually known for a few things, one of which is its football team, but also for some disasters, one of which has been the fact that the Titanic actually sailed from Southampton, and also this massive fire that we had about 11 to 12 years ago. Now, this massive fire was at this is a university campus, and this used to be the old clean room facilities that we had at Southampton. And because of that, we've developed a £250 million facility that is a small foundry that encompasses 8-inch compatible tools and really allowed us to develop some of the technologies that I was sharing with you today. Just as a brief introduction for Southampton and the group. So a quick outline of my talk, I'll go through the modern electronics challenges and what are the modern needs for AI. Memristive technologies, taking you through the technology, the tools, and the infrastructure. And I will finish by providing a couple of examples of how these technologies can actually be used. So we're starting by appreciating that nowadays we are surrounded by electronic devices that enable the IoT, Internet of Things revolution. And we know already that by 2020, we had 50 billion interconnected devices. Nowadays, we are closer to 200 billion interconnected devices. But our AI, our artificial intelligence, is as good as our access to data. And that's why these embedding these devices as broadly as possible is important. However, at the same time, these big data that are generated, the deluge of data, cause a significant issue in terms of the energy consumption that is required to support just the handling of this data, which appears to be even up to a fifth of global electricity by 2025. Now, one of the everyone has been quite vocal that the next kind of big thing in technology is that big data requires to have a hardware revolution, and really the engineering challenge is to address the classical von Neumann bottleneck, where we have the fundamental design of separate memories and processing capabilities, which actually puts a limit on what we can achieve. So that's what really Memristivs are looking at addressing, and I'll show you how. If we were to look for the way that conventional technologies operate. You have a processing unit, you have a memory unit, you go and fetch data from one to the other to do your computation and take it backwards to store it. But that creates obviously huge amount of traffic, and when data gets big, hardware finds it very difficult. So there are alternative solutions where people have tried to add memory, people have tried to add parallelism, and also new design concepts. But we've reached the point where everyone acknowledges that we actually do need new hardware technologies, and we need the ability to compute with ambiguity, as biology does. At the same time, we've actually been faced with the end of Moore's scaling law. Global Foundries has been one of the first foundries that announced that they're halted their deep submicron scaling of their technologies. And there's only so much that you can actually do at deep submicron technologies these days. So Memristive technologies promise to bring a new and fresh kind of era into this. First of all, we're starting by acknowledging that these devices are really small in terms of how small they can be integrated. What we show here is a chip that's been produced in my lab. On the left-hand side, you have an AFM microphotograph. Its side is about 1 micrometer, so you have 1 by 1 micrometer area in which you have 1,024 devices. So every single square that you see, every single knot that you see in this carpet-like type of structure is one of these devices. Of course, we've seen to the best of my knowledge, the smallest devices ever fabricated nowadays are down to 2 by 2 nanometers. So this simple two-terminal architecture allows for an extreme density, integration density, which goes beyond what current CMOS technologies can do. But at the same time, these devices are very popular nowadays because they are not only able to store zeros and ones as we would typically do with conventional memory technologies, but they allow to store analog memories. They allow to store a multitude of memory states per single cell. In this particular case, we've actually shown even up to 7 bits of memory states per cell. 5.5 bits have been the median response in a 1 kilobit array, as shown here. And before you ask me, yes, these are discernible memory states, so you're able to distinguish one state from the other, and they are truly non-volatile. So if you were to look in a couple of states that we selected here randomly, and also some neighboring states, over 8 hours retention, you still have discernible memory states. You do not sort of cross one boundary to the other. The beauty also of this technology is that once you have all of this fine analog tunability, you can use it as a tuning element, as seen here, and all it takes to program it is a couple of pulses or a train of voltage pulses that sets its resistance, a cell's resistance, to specific levels as shown on the top right graph. And you can also reset the device, and all of that operation only requires minuscule energy consumption. So it's in the order of picojoules to femtojoules. So overall, you have a technology that allows more for less, more memory capacity. It can actually be switched extremely fast in picoseconds, and also for less chip area, less energy consumption. But Memristive technologies actually act a little bit as integrating devices. And there is the so-called known time voltage dilemma, which is explained in this graph. So what you have is you start from an initial resistive state, you program, and you have many ways of reaching a certain final target memory state, either by sending a number of voltage pulses, as I've mentioned previously. In this particular case, 100 nanosecond wide pulses at 2 volts, or sending a single pulse, but which is, however, lasts longer. In this case, it was a 1 microsecond pulse. Or you can actually play by changing, like the amplitude of the pulse that you send. So it's essentially looking at the envelope of the stimuli in order to render different memory states. And that has been considered by many as being quite confusing in the literature, whether it has been a challenge or an opportunity. because typically for memory technologies, you'd like to have certainty that you would always hit the memory states that you wish to actually program. So I'll show you that there are loads of examples where this is in fact an opportunity for applications. But before we go to the examples, allow me to share a couple of minutes with you on the importance on having the appropriate tools and the appropriate infrastructure. So having the technologies themselves is not sufficient. You also have to have appropriate infrastructure. And we realized this early on from in my group. And we were not just using the standard characterization tools that companies like Agilent and Keithley, etc., are producing these days, but we went on and we developed our own characterization instruments that allow, at the click of a button, to characterize thousands of devices, either on a package, on a wafer, or even to do standalone characterization of these devices. This has evolved over the many years, and we started up, as your secretary mentioned in her kind introduction, a company called ARC Instruments, standing for Array Control Instruments, that is now operating to 21 countries globally. And we've actually supported over 200 groups internationally, including a big multinational company with their R&D demands for developing these emerging technologies. Why is this so popular? Because it's extremely easy to set up a characterization environment, characterize thousands of devices, get statistically meaningful results for the technology that you're developing, and you have a very friendly, user-friendly graphics user interface that allows you to achieve all of that. So our students really love it. On top of that, we've also developed a number of auxiliary modules that allow to control the environmental parameters such as humidity and temperature, with which you can actually do very easily without resorting to rather expensive instrumentation or probing setups with thermal checks and so forth. You can do very, very complex experiments with temperature, investigating temperature dependencies across devices, and also using these signatures of Memristive technologies to understand a little bit more about what is the underpinning switching mechanism of this device. In this particular case, we've shown that these devices, these metal oxide-based devices that we've been operating as analog memory devices, make use of an interfacial barrier control mechanism. Now, there is a second generation that is coming out now. We already started shipping the first instruments, which actually it's an improved version of the previous board. It's a rather new capability and has completely parallel read and write, as well as it provides access to selectors control for those who are developing 1T1R arrays. The beauty of this is that it's a general purpose instrument, like you have a 64 parallel SMU instrument without needing a switching matrix, which also allow you to do and characterize not just memristors, but all sorts of different type of emerging technologies or other standard technologies, TFTs and so forth, but even circuits. For example, you can even characterize DACs if needed. So with this type of instruments, this has been really essential for us developing and accelerating the development of certain Memristive technologies. And in order to be fair with how we benchmark the characteristics of these technologies, we've also developed appropriate testing routines that anyone can actually use. This is described in this first paper here by Stathopoulos et al., which is published about 2 years ago in Scientific Reports, and provides a very detailed, it's a kind of tutorial like of paper that allows you very detailed explanation of how to properly characterize the different switching characteristics of these devices. So starting from identifying what are the polarity dependence, the existence of switching, whether a device is able to switch or not, whether it supports any volatile phenomena, what are the underlying physical mechanisms, whether you actually require electroforming, and also you're able to extract parameters for developing your own empirical models, and I'll show you a little bit about that later on. And of course, you can run standard benchmarking tests on that, looking at multi-bit capacity, whether you have a truly analog operation, what's the retention of these memory states, is it truly non-volatile technology, and what's its endurance, how many times you can cycle between, cycle to cycle. And if you're interested more into this protocol, there is an additional auxiliary paper that describes also how you can use the same protocols in order to understand a little bit, just by electrical characterization of these technologies, to be able to identify the underlying physical switching mechanism in these metal oxide devices, which is described in this paper here. So moving on, different methodologies which are needed is, and we put quite a lot of effort with an Indian research fellow in the group, who's done fantastic work in collating all of the information that we've developed throughout many years in our group. And because one key question is, you have these technologies, but how can you actually design with along with CMOS technologies, especially when you integrate them on the back end of line with CMOS technologies, as we do at Southampton, and how you can develop new circuits. So this particular two-part paper describes exactly how you can go about modeling and verifying and all the verification steps, and presents also how you can do simple circuit schematics and layout. So you're starting from an explanation of the different technologies. How do you model this? How do you actually benchmark, and how do you introduce this into the design flows, into the design flow of the standard PDK, develop your own P cells, and develop your own layouts in the end. So I think that's a nice tutorial, kind of two-part tutorial paper that takes anyone from the basics to the more sort of advanced concepts of designing this. And because we don't have enough time, I just thought that I'll share with you a couple of useful behavior models that we've developed over the years, some empirical models that we've utilized these previous capabilities that I've shown. The first two look more about the temperature dependence of these technologies in the switching operation. So when you use them as non-volatile switching elements, and the first part describes a behavioral model, where the second one is a more physics-oriented and inspired model. The third one and fourth one look at the volatile. How do you model, how do you characterize, and how do you model the volatile characteristics of these technologies? The one by Stathopoulos explains what happens when you have switching uncertainty. How do you model the noise in the switching of a device? And the one by Messaris provides the bare bone, if you like, model for a Verilog, a model that is essentially important to have when you're looking at crossing boundaries and developing appropriate circuits with design tools that exist that are commercially. And the rest of the models cover different aspects. They cover volatile characteristics, activity dependence, and starting all from the standard, more conventional, if you like, model that describes the window function that was introduced about 10 years ago now. So with all of this in mind, the technologies, the infrastructure, the tools and the models, I want to show you a couple of applications that we've been developing that allow us to bring AI closer to the edge with these technologies. So the first example has to do with running in silicon machine learning implementations with these technologies. So starting from the left-hand side, you could see a chemical synapse depicted. And essentially what the chemical synapse does is you have two terminals. If I look at it as an engineer, I would argue that you have two terminals, a pre and a postsynaptic terminal, a barrier which is denoted as a synaptic cleft, within which, when you have an activation from one of the terminals, you have the release of neurotransmitters, and that is the source of memory in biological systems, as shown by Kandel, who won a Nobel Prize in Physiology for this discovery. And when I look at this cross-section of a synapse, again, abstractly, I can argue that this is rather similar to the cross-section that you see here on the right-hand side, which is a stem cross-section. When you see in blue the two electrodes of the device, so you still have a two-terminal configuration, a top electrode and a bottom electrode that represent the presynaptic and the postsynaptic terminals of a synapse. And in between, quite similarly, you have a barrier, which is denoted here as green, which is nothing more than titanium oxide. The green is titanium, red is oxygen species, and you have the diffusion of neurotransmitters in there. So whether you're looking at organic or inorganic matters like that, the dynamics appear to be rather similar. So here's the first example where we took these devices, we introduced them into a winner-take-all configuration as shown here on the left-hand side on my cursor, and you have probabilistic neurons that allow you to learn different patterns with good confidence. Probabilistic neurons also allow you to handle mistakes rather well. And we've demonstrated in this paper for the first time that this type of configurations that run on analog memristor weights are excellent architectures to allow you to run unsupervised learning. Unsupervised learning is particularly useful for continuously on systems where you have the different patterns. You're not necessarily sure of what is it that you're looking for. And also the other important parameter is that the class centers of this data moves over time and they drift over time. So they are able to learn in their own kind of way the different patterns and also learn to adapt so that they can follow these class centers that they drift over time as shown here. So you see in the graphs in the middle, you see the different weights of the memristive synapses. And you see also the initial and the final responses of the neurons in the different patterns that were in that they were inherent in the data that were presented to this particular configuration. And as you could see, this drifts over time, and you're able to actually, the neurons are able to learn the new patterns as they are introduced. So a second example has to do with an ability to use memristive devices as threshold integrators to process big data at the edge. If we were to look at how these memristive devices work, you have essentially two important parameters that one has to consider, two sort of switching thresholds that one needs to be aware of. A soft breakdown below which nothing happens, this is in voltage. So below this switching threshold, nothing really happens, no switching is observed. As you can see here in the two graphs below, the bottom graph shows the resistance, the transient response of the resistance, and the one in the middle shows what happens when you send positive and negative pulses, and the green and red bars denote the switching thresholds of this particular technology. Now, when you are above this soft breakdown, magic starts to happen, where you start seeing that depending on the amplitude and the energy provided to the system, you're actually registering different analog memory states. And this other hard breakdown we intentionally avoid here, essentially above this, but we have to be fully aware of this because above this threshold, there is irreversible switching. Yes, you often observe very nice pinch hysteresis loop and signatures of memristive devices, but these are only one-off characteristics, and we have to be really careful on what we attribute as a useful device. So what we've done with this particular attribute and this particular characteristic of the devices, we've used them as a thresholded integrator. That's essentially what happens here, right? So we've shown to the devices, we bias the devices with biosignals, electrical recordings from neurons cultured on multi-transistor arrays. We recorded those signals and we played them back with an offset applied and a preamplification applied to these signals to make sure that we bring those action potentials just above the switching threshold of these devices. What that has as an effect, as a result, is that you register every single of these spiking events, which denotes the activity of a neuron, as a change in the resistive state of the device. And if you were to repeat this recorded signal, so we concatenated and copied it in 4 times, you will see that, and inverted it, you see that, it's reversible, it's fully reversible. So without knowing anything about the signal, how many spiking events we have in here, we could see that we can passively look at the overall change of resistance of these devices, and with that denotes essentially the amount of activity that that neuron has actually expressed. So why is this important? Because you don't have to have a continuously on system to register these spiking events. You minimize all of this noise automatically, which is due to multiple sources of neurons existing in a system. But that is all automatically filtered out because it's sub-threshold, and you are registering every of these single spiking events in a passive way as a change in conductance. And that, as a result, has a significant reduction in power per channel. We've demonstrated that you can actually do about 2 to 3 orders of magnitude better than the state of art of a CMOS counterpart designed for spike detection. Now, spike detection is not the only thing that matters here. Remember again the previous point I've made about the time voltage dilemma. The fact that the spikes look, they can have all sorts of different shapes depending on where they are being sourced from. And spike detection is something that is important to do in electrophysiology, but also spike sorting is important, being able to know which type of spiking event you actually have. Well, guess what? We can still use single devices and the physics of single devices to allow us to understand that and to do spike sorting at the device level, because the corresponding change of resistance is relative to the envelope of the spiking signals, as you see here. And because of that, we can actually plot, we can use a number of different spiking events. Here is on the right-hand side, a mixture of the spiking types. Here is in a more structured way, where you have spike type 1, 2, and 3 repeating over time. And what happens is that if you were to plot the relative change in conductance or resistance with respect to the initial resistance, these clusters automatically appear. And why is this important? Because otherwise we would have resourced all of this template matching, if you like, to a supercomputer externally that is obviously not a very efficient way of doing this, especially for implantable systems. A different example has to do with a biohybrid system that we demonstrated literally last year, where for the first time we linked a real brain with a silicon brain. And this was the output of a European project that we've carried out with some colleagues from the University of Padova and the Institute of Neuroinformatics in ETH. And what we've actually done is we've linked in real time the responses of rat neurons via memristic synapses that were used as the neuronal bridge to link the biological and the artificial intelligence and the two dissimilar worlds. So we were capturing the action potentials of rat neurons cultured on a Petri dish on multi-transistor arrays again, with and then using memristive devices as the neuronal bridges that modulated the signals and allows to stimulate silicon-based neurons via CMOS technologies existing in Zurich. And then we will also record the response from those neurons, modulate them again by memristive weights, memristive synapses, that allowed us to go back and stimulate in real time the real neurons. So to the best of our knowledge, this has been the very first demonstration of a bidirectional, geographically distributed biohybrid neuronal network. A fourth example has to do with how do you run some of the energy costly operations in silicon, and whether you can actually do something with these memristive technologies, and specifically for Bayesian inference. Well, we looked at these crossbar arrays that we've been developing, which are, even if you were to use them without any passively, multiplication is perhaps the most expensive operation that you can actually have when you try to implement this in hardware. But guess what? These passive arrays of memristive devices are perfect for enabling, in a very energy efficient way, vector matrix vector multiplication, or even scalar multiplication if needed, simply by using Kirchhoff's law and adding the currents in these columns and using these weights for developing, essentially, for rendering the operation. A next example has to do with how can we go beyond the current electronics design paradigms and develop different design paradigms. And we need to consider that really our world is analog. We are surrounded by analog signals. All of our sensors utilize analog signals continuously. We see, we smell. We don't do that with fixed data precision. But at the same time, for historical reasons and for energy efficiency purposes, and with the scaling of CMOS technologies, our electronics, our mainstream electronics, is mainly developed via digital technologies. Well, we've asked the question, what would happen if we were to take one of the fundamental computational, which is a digital gate, as shown here, a standard inverter, and integrate within this circuit these analog memory technologies. Well, you will take the standard transfer characteristic of this inverter and you will skew its transfer characteristics into something that looks, that is able to compute analog signals. And not only that, you're also able to go and reconfigure the weights of these devices so that you can choose to maintain the balance between the different weights, or you can choose to arbitrarily select those weights here, which allows you to change and to skew the transfer characteristics and shape this analog reconfigurable gate. So it's now an analog reconfigurable gate very efficiently. And how efficiently? Almost at the cost of digital. So the energy consumption still here is extremely efficient, as it is with the standard inverter. And besides that, we've also developed some very primitive readout circuits that allow you to use this concept to do plane splitting in silicon. So you can use it for classification, where you can store the values of particular data that you're looking for in the weights of these devices. And the beauty of this approach is that whenever you hit the target, the device would actually, this system will tell you that you found the value that you were looking for. However, when it's away from that, the system will consume minimum power consumption, and at the same time, it will show you which way you need to move in order to find these parameters, these values. And this is just a similar example to what I've shown previously with the data classification of spiking events. This has just been used as an example. In the end of the day, you can utilize it with whatever data for image processing, for natural language processing. And we've implemented a number of these template matching pixels, that's what we call them, texels, in a cascaded fashion that allow you to monitor these values and recreate these patterns. So moving on, as a final example, I'd like to share with you that how these technologies can actually be competitive in terms of implementations for low power radiation hard technologies. When we talk about harsh radiation environments, quite often we're thinking about stuff that have to do with nuclear energy or the defense sector. But besides that, there is an ever-growing need for using and developing electronic systems that can withstand harsh radiation environments for a variety of different applications, for scientific discoveries, which has to deal with very delicate instrumentation, for healthcare type of applications, even for autonomous vehicles and advanced servers, all the way to putting stuff in orbit and systems in orbit, and for space exploration, as shown in this figure on the left-hand side. And there is a variety of sources of radiation that contribute to this challenge, if you like. Now, there are three main kind of physical causes why systems, electronic systems, tend to fail. Have to do with the total ionization dose that systems undergo, displacement damage, and also single events and the effects that these actually have to the behavior of a system. There are mitigation strategies for standard electronic systems, whether we work with a layout, making the channels of our transistors shorter and narrower, whether we are protecting them by enclosing guard rings, and also at system and circuit level, there is a lot of work that's been done in terms of redundancy, but all of that requires additional resources. The most important parameter that leads into the failure of these systems is the different memory technologies. And in this review paper in Nature Electronics that came out earlier this year, we've shown how different established as well as emerging memory technologies like MRAM and resistive RAM compare across the different parameters, across single events, TID, power efficiency, non-volatility, speed, and density. And because of the ionic nature of the switching, and that it happens also mainly in the bulk of these devices, it appears that these emerging technologies are more immune to radiation effects. Now, what are the challenges and opportunities? There are still loads for all of us to do. And we've published this paper in Nature Comms a few years ago, but it still remains relevant, where we've identified that the integration of these technologies with CMOS technologies remains an important challenge. And we still need to address the variability of these technologies, the latency that they are actually is introduced also with integration with standard CMOS technologies. What's the density aspects? What's the technological feasibilities? And there are a lot of parameters to consider: the cost, the different device architecture, whether you go for a vertical, for a plug via, for a cross point, and so forth. So there's really a lot for all of us and for the community to still work on and develop further. And just to conclude, I'd like to show you that although we covered and Memristive technology has been put in place mainly as a next generation emerging data storage technology and also for charge storage, there are a lot of other applications that emerge that are now revisited because of the dynamics of these technologies, and haven't really had the time to go through this. But there are papers that are appearing in the literature where you can use these technologies for chemical sensing, for temperature sensing. I mean, I've already explained how you can do that, how you model the temperature dependencies of these devices, even for tactile and light sensing. That render different applications in healthcare monitoring, all the way to bringing AI to the edge, where you have emerging capabilities for pattern recognition, for image processing, for data clustering, and all the way to autonomous decision-making systems. So hopefully the application examples that I covered today give you a glimpse of how we can put these different components together in order to get to this long-term ambition. And if time allows, I'd like to share with you a very brief 2 minutes video that shows the next kind of generation of systems that we're developing in the group and the challenges that these are addressing.
Artificial intelligence is transforming.
Excuse me, Professor. Dr. Saibal Mukherjee has a question for you. He is raising his hand for some question.
Sorry?
Professor Mukherjee is about to ask a question. He is raising his hand for some question.
Shall we see the video first, and then that concludes my presentation, and then I'm happy to take any questions. Is that okay?
Yes, sir, it's fine. It's fine. Okay.
Can you hear?
Artificial intelligence is transforming the way we interact with the world. It allows us to automate routine tasks and even augment our abilities. Over time, the use of AI broadens, but so does the amount of data generated, driving current infrastructure to its limits, demanding ever more data bandwidth and energy. We address this problem at its source, embedding intelligence everywhere by delivering AI on chips. Our solutions are powered by a new electronics fabric that we have developed over a decade of research, which uses nanotechnology to achieve computation, memory, and energy performance impossible to deliver by modern electronics. To support the creation of intelligent machines, our AI chips enable 4 core capabilities: intelligent sensing, pattern recognition, online learning, and reasoning. Our sensing chips address the power and bandwidth challenges of big data by compressing information on site, allowing monitoring more sources in parallel. Our pattern recognition chips empower local classification capabilities, minimizing the need to share sensitive data online. By being less dependent on cloud computing, these emerging AI systems are able to react faster, allowing to make critical decisions in real time. Modern electronic systems are progressively operating continuously and often need to memorize events quickly and over longer periods. Our advanced learning solutions can support such emerging needs without saturating memory resources. Our solutions are designed in ways that they can empower machines to reason and apply logic and common sense like humans do, enabling them to use judgment when dealing with new situations. These core capabilities pave the way towards intelligent machines that are destined to revolutionize the use of AI in serving modern society, enabling smart assistants, autonomous vehicles, and neuroprosthetic devices. All made possible by our vision for embedding intelligence everywhere.
So hopefully that provides a glimpse at the challenges that we can overcome with using these technologies. And we're really grateful to the funding that we have received from both the European Commission as well as the EPSRC and the Royal Academy of Engineering and Royal Society, particularly the Royal Academy of Engineering that is supporting the development of AI chips with Memristive technologies. And they all of them support this fantastic team that you see in this slide, who have contributed in different aspects of the work that I presented to you today. So with that, I would like to thank you once again for the opportunity to talk to your to the IEEE NTC at India, and I will be really delighted to take any questions.
Thank you, Professor Themis, for delivering such a wonderful and knowledgeable talk. Participants, now the floor is open for discussion.
Yes, Ruchi, so can I ask one question?
Yes, sir, you may proceed.
Okay, thank you. So, yeah, Professor Themis, thanks so much for joining us in this event from IIT Indore. This has been a great talk and we learned quite a bit. And I think one of our students is already in touch with your company regarding the procurement of the product that probably you have already discussed about. So a few things I would like to know from you, since you have vast experience in the particular domain of this. specifically to neuromorphic systems and also bio-inspired, applications of our RAMs that you have shown only glimpses. So one thing is you mentioned that you did some culturing of the neurons and then tried to get the signals and then you fed it across or probably make your artificial neurons learn about those signals through some existing CMOS. I think something you have mentioned that exists in the lab, but actually I could not follow. Probably you, due to the time restriction, probably you might not be able to show the entire glimpse of it. So I would like to know how you did that in your lab.
Yes. So maybe I can share my screen again.
Okay.
So I don't know if you can see this slide.
Yes.
Right. So we basically had three different components. So we had multi-transistor arrays that we used to culture the neurons on, and that was done in Padova. And those multi-transistor arrays have been used as the neural interface to detect the spiking activity of these neurons. The second component was the Memristive synapses with the ARC instruments board that we have at Southampton that was sitting at Southampton. And then the third component that we had was the leaky integrated fire neurons that we developed. Our colleagues at the Institute of Neuroinformatics, led by Giacomo Indiveri, have developed with standard CMOS technologies. So we had three very different components that allowed us to do this bidirectional seamless integration of intelligence. So you had real neurons talking to artificial neurons, but connected via memristive synapses. And the beauty of this was that this was actually done over the web. Rather than, there's a lot of effort of putting some of these concepts all together. And in fact, we've been working on that as well, to have a monolithic implementation of the chip that allows you to do both the interfacing as well as the CMOS, the neurons computation on the back of this. But in this case, because also of the pandemic, we felt that we should also continue with the experiments that we were doing, and we did it over the web via UDP protocols. And I should actually point you to this paper. I forgot to put here update this with the actual citation, which it appeared on Scientific Reports last year, and it was amongst the top 3 most downloaded papers, because for the first time we've actually integrated biological with artificial intelligence in real time.
Yeah, this is really interesting. Yeah, thank you so much for
Sure.
discussing a bit about it. And
the key question that we've asked here was that we have a technology, the memristors, that speak the same language with biology. So since we have that, why don't we use it as the interpreter? Why don't we use it to link to biology? And I think this was the key kind of, if you like, innovation.
Yes. Yeah. And thank you so much, Professor Themis. The last question from my side is actually like one of our activities happening in our group now regarding the image processing. That is the final application that you have shown. So we have actually trying to do several different algorithms like discrete wavelet transform and then TWT. So those things we are trying to do and trying to integrate our Memristive model that actually one of our students have also done some analytical modeling on the crossbar. So our memory is mostly on ITRIA based system. So we developed a model and then tried to integrate along with our entire flowchart for the image processing. And after that, we are getting the decompression done, and we are just actually measuring PSNR and SSIM, those improvement factors, and we found really excellent results. So we'd like to know from your side, like, is there any data available in the industry or maybe in the academia in which we are also try or we can get some estimation in terms of the cost effectiveness and the saving in terms of the power, if we are actually trying to incorporate this crossbar with the existing CMOS technology?
Yeah, that's a very good point. I mean, there are before I show you this example, I'd like to make a comment that which we also receive very often from referees when we put out papers for consideration, and the argument could be, you know, like this is still not competitive with 22 nanometer CMOS. All right, so we have to be a little bit careful on the way that we do these comparisons, because, you know, we need to compare apples with apples, not apples with oranges, right? In the case of the biosignal processing that I've shown you, you know, like the system that we had, which was based on a hybrid implementation, was at least performing at least 2 orders of magnitude with better power consumption. Okay, and then again, it will be questionable whether you can do better with just digital at 22 nanometers, for example. So I'm not fully aware of, you know, like any data that one can actually use. This is a constant challenge that I'm afraid you would also have to bear with and provide enough confidence in data to show that your system, you know, is competitive, right? When you scale it down, when you do all the different tricks that you know modern technologies do. There are two areas that I can point you to. I've done rather similar work. In fact, it's interesting because just yesterday someone was asking me for this, and I published a paper over 10 years now, 12 years ago, I can't remember, where we were looking at modeling the outer plexiform layer of the retina. I'm not sure whether you are familiar with Carver Mead's original work with diffusive resistive grids. All right, so we had a paper with Memristive, diffusive Memristive grids, and we were showing the benefits of this, and that was about 12 years ago or more. I'm happy to send you, you know, like copies of these papers. We've also shown how you can actually do with Memristor models, how you can use those to do processing of videos in real time. Okay, the other component that is interesting is new technologies that start appearing that are light sensitive themselves. Okay, and this is just one example. I mean, there's a lot of work out there, but in fact, this table shows many references from the literature on where they have used light sensing materials as the active core of the memristors, and that obviously has allowed people to, you know, trigger a switching activity with modulation of light. In the particular example that we have in published about a year and a half ago in scientific reports, we've taken a very different approach. We've used non-light sensing active materials, but we've functionalized those memristive technologies with on the top electrode we introduced P.PSS, which is light sensing, and in fact it also shows a wavelength specificity. So that's why I concluded with that slide where I've shown that there are many other opportunities, because with this principle of functionalizing memristors, you're able not only to create a light sensing memristor, you can create a neural interfacing device, you can create a chemical sensing device, and in fact we've shown this in some other works, which again you can find in the literature a couple of years ago, where you can functionalize memristive technologies with antigen specific antibodies and turn them into very efficient chemical sensors. So you know, I gave you a lot of different examples here, but hopefully that shows how rich this field is, and that it calls for all of us to contribute different innovations. And certainly image processing is something that is very important for surveillance and for security applications. And I think it's certainly an area where power efficiency would be better from existing systems. There is additional benefits because by creating all of these power savings, you don't have to rely on computational power up to the cloud, and you can do all the processing locally. And that opens very interesting follow-up considerations because you don't have to share your data with anyone, and that's intrinsically a secure option.
Thank you so much, Professor Themis. Thank you.
Any other queries from the participants?
Good afternoon, sir. Jyoti here. I have. Am I audible to all?
Yes.
Yes, Jyoti. Yes, Jyoti, you are audible.
Thank you. Thank you. Sir, I have question from your slide number 25. You mentioned some Memristive neural network using hardware 1001, software 1001. So I want to know what it represent actually.
Right. So in this particular case, we had these different patterns that we were looking for that were embedded essentially in the data. Right. So we have a spiking activity detected by the input neurons, and essentially we were looking for these different patterns, right? And we wanted these output neurons to be able to classify those. Okay. Now, what the winner-take-all configuration shown on the left-hand side with interconnections made out of memristors allow us to do is allows to the system to optimize the dynamics over time to be able to detect those particular patterns. So what you actually see here is at the initial response, there is no specificity to these patterns, and after the training of the system, the self-training essentially through recording this data has occurred, the neurons, the output neurons are able to distinguish those particular patterns.
Okay, so sir, means this Memristive neural network is replacing a kind of ResNet 50 model or AlexNet model or something else it is?
You can use that, you know, like, I mean, it's not replacing per se. It's not fair to say that it's replacing. It's more of a an alternative way to do it, right? I mean, in silico.
Okay. So, sir, you are using software tool or some hardware implementation is there in this work for recognition this pattern of 1001 or 0110?
Correct. We're using both. So we're using, first of all, hardware, which is the Memristive synapses, and the ARC neuro, sorry, the ARC1 instrumentation that controls the memristors, and then the neurons and actually some of the synapses as well were implemented in software on
Yes,
the on the microcontroller of this system.
okay.
But nothing stops you, obviously, to do that. Ever since we published this work, there's been other groups which have been following this work, and they've implemented, you know, like a full monolithic implementation that does everything in silico.
Oh, so actually, we have done the same work using software tool. Means we try to modify that activation function by our window function of an analytical model, and then try to recognize this pattern of 1001 and 011. So I just want to relate this work with my work, that whether we can modify this activation function and can do the same things or something else you use in your software tool.
Perfect. In fact, something that we are currently working on, and we're about to release a paper on that, is that on the back of this system, we've developed our own simulation platform. We call it NeuroPack, that allows people to run any of those plasticity rules, neuronal models, memristor models in this software package. Which is also compatible with the instrumentation board that we have developed, and many groups actually have, even in India. There are tens of groups that they have that, which allows you to run and simulate everything with fantastic flexibility, because you can use different memristor models, different, you know, configurations, and then run everything with the devices in silico.
Okay,
So,
thank you, sir.
If you contact me in hopefully about 2 weeks' time, I will be able to send you a copy of that paper when it comes out.
Thank you, sir. Thank you so much. Sir, if you permit me, I have one more question from slide number 33.
33, sure.
Yes, sir.
Yes?
Sir, in this crossbar, can we store images? If yes, then what's the process? Can you explain it stepwise? Like how we can this supply this pulse voltage through rows and then collect from columns. I want to know this part.
Yeah, it's, right. So if understood it well, the question is how we can individually program a cell in here. Is that correct?
Yes, sir. If I want to store image of 256 cross 256 resolution in this crossbar, then
Yes.
what's the process?
Yes. So the
Yes.
process in this particular case, because this was a passive crossbar array, all
Yes,
right, just as an example, it might be a little bit more difficult because you would have issues with sneak path currents. So, you know, when you try to access a particular cell in a column, in a row, you might also disturb the states of adjacent cells, right?
Yes,
However, by using 1T1R configuration, so using selector topologies, it could be 1T1R, it could be other, it could be 2T1R, there's many different flavors. You are able to fully isolate those cells, program them to the resistive state that you would like them to render, and essentially store, you know, like use that approach for storing, you know, your data on a crossbar array.
Okay, thank you, Professor. So
Thank you,
one
sir.
question from actually the chat box is from Mohammed, from Professor Scott Griffith, University of Cambridge. Basically, he is asking about the how do you feel about
Sorry,
the rootless
I missed.
scalability of interface barrier switching?
Can you please repeat? I've missed the first bit. If you don't mind repeating, please.
Okay,
I'm
okay.
here, so I can ask my question first.
Okay, okay. Please go ahead. Please go ahead, Mohammed.
So, hi, I'm Mahmoud. I'm a group at Cambridge. I had a question.
So, Mahmoud, if you can please a little bit louder because you are very faintly coming across. Sorry.
Yeah, sorry about that.
That's better.
Yeah. So my question is about interface barrier control method. How you feel about them?
Yes, so that's a very good point. I mean, the interfacial barrier control, we have significant evidence to show that is the underlying switching mechanism for supporting the analog memory states that we've seen. So up until let me see if I can share my screen again. Are you able to see my screen?
Yes, yeah.
Yes. So up until recently, we were able to observe a number of different memory states that can be supported on individual devices, but this was done mainly via different switching mechanisms that were more bulk oriented. For example, you would have the creation of a filament, the reduction of a certain area that also creates a filament macroscopically. But that provided, in my opinion, somehow a limited kind of performance, if you like, on the number of memory states that you can store in these devices. Now, by using this interfacial barrier control, something that I haven't explained here because of the constraint of time is that this behavior we were able to engineer and to develop by introducing a bilayer configuration in the devices. So previously we have mainly focused on developing a number of different titanium oxide based or single layer active materials based devices, and the switching was occurring in the bulk or by using an electrochemical metallization cell that will diffuse the ions from an active metal, an active electrode into the host material. But as I said, that had rather limited analog memory capacity. When we played with a number of different bilayer configurations, alumina with titanium oxide seems to be working quite nicely, which was also acting as an oxygen reservoir. And the signatures that we've observed from the electrical characterization that I've shown here basically allow us to fit the data in such a way that denote that there is a presence of an interfacial barrier, and that by programming it, we are able to control the interfacial barrier that is created there. So that is done in a way indirectly through these temperature-dependent measurements. that we've done.
Yeah, I have read Maria's paper, I think, on it. Was my time in,
Pardon?
I think Maria, which was part of your book, had published on this Wiley configuration layers, not just Wiley, been up to 10 layers. I was mostly because I'm a materials person, so I'm interested in the switching mechanism. I believe that there is a debate to be had with the ionic effects or crush coupling.
Mahmoud, I'm really sorry, I cannot hear you well.
Can you be a little bit loud?
Yeah. So I said I read the paper by Maria on this devices and use of different layers. I was interested in essentially the retention properties of many layer structures because I don't believe the retention was quite, at least there wasn't much data retention property of the bilayer structures. Can you comment on that?
So on the ones that I've shown previously, you mean?
So I think there was a paper by Maria on.
Sir, can I ask you a question on behalf of Mahmood?
Yeah, yes, of course. If
He was asking that there is a paper of Maria who it was describing about retention, and he want to know how this retention was specifically described in that paper.
I'm not exactly sure which particular paper Mahmoud is referring to. If the question is about the bilayer configuration and the retention data that we've shown here, I mean that provides already very good evidence that you have a physical separation of these memory states. I mean, 8 hours, I know it's not long enough with regards to other data that might show years, for example, or they might show, like days, right? But the purpose of this was to demonstrate that you have substantially good retention across very closely packed memory states. I mean, you could see that sorry, it keeps changing. The dynamic range of switching here is rather small. So you are between, like a 50 kilo ohm sort of regime, and yet you are able to maintain these states being discernible. Has that answered your question?
I think it does, yeah.
Mahmoud, I would be happy to also discuss this offline if you feel that, there is something further you're interested into this.
I can send you an email, yeah.
Very happy to respond.
And the Professor
Thank
Themis, basically the time is running out actually. So basically we have the last question from the chat box, and then ask the last question is that's related to the computation in crossbar array architecture basically. So it is basically the analog, digital, or mix of the signal, the computation in the crossbar architecture.
Yes. The computation in the sorry, what was the question?
Basically, question is the computation in crossbar array architecture is analog, digital, or the mixed signal.
That's a very good point. Well, it depends on the technology that you have, right? But we've actually had quite a few papers lately where we've shown that one of the big benefits of this particular metal oxide technologies is their analog computation that you can have. So there are examples that came out from my group as well as other groups that they show how you can use this for doing threshold logic gates, for example, or how you can do the analog mixed signal type of computation that I've shown, the analog reconfigurable gates that I've shown in the other Nature Comms paper that we published. From my point of view, I think it's important that you have an analog reconfigurable engine, and then depending on the signals and the applications that you have an interest in, you can either use it to classify digital signals and to process these digital signals, or analog signals. So you can have analog in, analog out, analog in, digital out, and so forth. So I think that's kind of really, and the analog in, digital out is sort of a threshold logic gate example I gave previously. But all of them sort of benefit from having an analog reconfigurable engine.
Okay. Thank you, Professor Themis. And now I request to Ms. Ruthi, please go ahead with the close the session, and then thanks note for the speaker.
Thank you, Professor Themis, for the wonderful lecture. And now I would like to thank all our sponsors for constantly supporting us and our chapter. At the last, I would like to thank the participants for actively attending this lecture, and also our teammates for successfully organizing this event. Once again, thank you so much, sir, for being with us for this lecture. And with this, I would like to say goodbye to all the participants. Thank you.
Thank you very much for your kind invitation, and thank you for the questions.
So it's all our pleasure.
Thank you, sir.
Bye now.
Yeah. Bye, Professor Themis. Yeah.
Thank you.